yeah, I personally thought this was like a pretty hard silver contest. The problems are super ad hoc. Yeah, they're not easy to solve like very fast. Uh, Personally for me, it took some time to come up with the solutions compared to other silver contests. But yeah, Clash was kind of a problem, like a simulation problem. Like basically, I'll talk about the problems in detail more later, but most of the problem was about like figuring out how to do the simulation faster. Yeah, and then milk buckets. Yeah, I put it under ad hoc slash math. Um, yeah, and then point elimination. Yeah, this is probably the trickiest problem, and at least for me, and the most interesting problem. Yeah, so this is pretty ad hoc. There was some greedy stuff that involved. Yeah, but let's get into the contest. Um, yeah, yeah. So I think problem one. Yeah. So the idea of problem one is like you do a greedy strategy, and then you want to simulate it fast to make it work fast enough. Yeah, let me rearrange these things. Uh, Give me 1 second. Okay, all right, great. Um, yeah, but basically the idea for the problem for problem one is uh yeah. So you can just do a greedy, right? So in the case where uh yeah, so the problem it says that if there's at least one win condition, then the next card you play must be a win condition, right? Um, so if there's a win condition, we're just gonna be greedy, right? Yeah, pick the cheapest. Yeah, yeah, like the cheapest one. Like basically you have like zero elixir and you just wait until you have enough elixir for the cheapest one and you take that, right? So if there's a win condition, then pick the cheapest one. Otherwise, pick the cheapest non-win, right? Yeah. Uh, yeah. So I think if you just, yeah, if you implement this directly, since T is like, I think the queries are pretty large, so you're not going to get any of the subtasks, but let's just consider this greedy, right? And how to make it faster, right? Um, yeah, so yeah, so yeah, so basically, like one thing you can observe is uh, like let's say you pick, consider like the sequence of things that you pick, right? So maybe you pick A1, A is already taken, so B1, B2, B3, B4. And then you're going after some point, this greedy strategy is going to keep cycling. Um, and the length, I think you can show the length is like n minus h, but you don't really need to worry about it as long as the length is small. Like you can get your implementation to make this work. But basically the strategy then becomes like like you find this last cycle, right? And then you have this t as an input. And then basically you're going to repeat the cycle many, many times, right? You're going to repeat the cycle uh, right? And then maybe you'll repeat part of a cycle. And this is the last place, last one, last card where the time is less than or equal to t, right? Yeah, so you're gonna keep drawing cards and you're gonna pay like different amounts of Mulixir. And then at some point you're gonna reach a cycle, and then you can just like calculate an O of one, like how many cycles you actually need. And then there's this last part that's like part of a cycle, right? So that's like a high level idea for how you can like approach this, right? For the actual implementation, yeah, maybe you don't need that much this much, but I just like calculated the first 26 uh yeah, first 26 cards. So you can just imagine there's a list of the first 26 cards, and then consider like the cycle that ends at the last place, right? And then yeah, and then you can also have like a vector of there's not a great straight line. Okay, yeah, whatever, it's better. I guess not really. Yeah, so you can have a vector of the total wins. So you can think of this as like a prefix sum, right? So like at the ith position, this is the sum of all of the wins, like zeros or ones, until the ith card, right? And then you can also, yeah, so there's just one way to implement it that felt convenient to me. So there's a total wins, a prefix sum, and then this is the total time, prefix sum, right? Um, and based on the first 26 cards, so if the query is like less than 26, then you can just yeah, you can just do the binary search on the time and then find the total wins and you're good. So we care about the case where the time is pretty large, right? So we have the total wins. It's like a prefix sum, like prefix like total wins for the first I cards, and then total time that it takes to get the ith card, right? And then you basically consider the last cycle, right? And then the length of this, like the amount of time, the length of the cycle in terms of time is going to be this value minus this value, right? And given this query, that's the time, this will allow you to determine how many cycles there are, right? So you can determine how many full cycles there are. So there's all these full cycles. And then there's also this partial cycle, right? And to actually calculate the length of the partial cycle, you know how much time you have left from here. So you do a binary search over this part. You do a binary search over this part to find like the last card that you're going to draw in that time, right? So you can think of this as whatever you pre-computed plus a bunch of full cycles plus a partial cycle, right? And then to find the total number of wins, then you just take the prefix sum of this and then consider the prefix sum of any cycle, multiply it by the total number of cycles, and then you also have the length of this partial thing. So it's going to be this subarray sum, uh, or like the difference of this value and this value will give you the total number of wins, right? Yeah, any questions? I'll just summarize this. Yeah, so for this problem, there's a greedy strategy. And the main part of the problem is how you simulate it fast. Yeah, and basically you can show that you're going to keep cycling. Um, yeah, and then you care about like the total number of cycles you make after whatever you pre-computed. So and to do that effectively, it helps to store like the total time for each card that you get, right? And you can use that to calculate the number of full cycles, and then there'll be some partial cycle, and you can binary search over this array to find like how many cards you're going to draw for the partial cycle. And then we can calculate the rest using prefix sums, or using the prefix sum of all the wins. Sorry, I did not read the chat. How do you know when the cycle starts again? Good question. Yeah, so yeah, one way to do that, I think you can show that it's actually n minus h, but like even if you don't show this, like uh just consider the final element of whatever you pre-computed, it's equal to x. Um, and then the element over here is equal to x. Um, I haven't actually tried like proving like when it converges, so I'm actually not sure. But um, yeah, maybe you don't need 1e6. I think the reason I put 1e6 is because n is up to 2e5. Uh, right. Maybe you can prove something. I'm actually not sure, but maybe you can prove that like instead of 1e6, you only need like 5n or something. But based on the fact that some of the inputs are 2E5 and it worked for 1E6, this suggests that it like converges fast enough. But I haven't tried formally proving this part. Yeah, so in some sense you can think of it as proof by AC. Yeah. But yeah, maybe there's also a way to like argue about when it converges. Yeah, so I think like when I was actually doing this problem, I was getting wrong answer. So I was like doubtful that this is actually the right approach. But then I just found some bug, like small bug, and then it worked. Yeah, but I didn't try to think too much about how to actually like prove things for this problem specifically. All right.